Soaring aspirations. This is the Biostats Core Special Topics Talk 13, Multi-Level Modeling for the Uninitiated. I'm Mark Williamson for the DaCCoTA project at the University of North Dakota. Our goal today is to understand multi-level modeling, gazing at the expansive rafters of such levels. To facilitate this, I will cover definitions and common types, aka a view from above, designing and setting up models, blueprints and bricks as it were, results and caveats, open the doors carefully as you please, conceptual examples, an awe-inspiring tour, and finally, worked examples, going the distance. Before moving on, please take a moment to take the pre-test. Also, once we get to the coding section, if you'd like to follow along with code, the R code and SAS-code are available here. What is a multi-level model? One definition would be it is a statistical model applied to data collected at more than one level in order to elucidate relationships at more than one level. So simply put, multiple levels of data. We'll get more into what we mean by levels, but for now let's move on. Now, you may have used a multi-level model before but not known it because there are many different names for it. A lot of different aliases like linear mixed model, mixed effects model, hierarchical models, nested models, repeated measures models, random effects models, random coefficient models, etc. One of the reasons for this is because different disciplines use different terminology. For example, nested is a much more familiar term to ecologists, like my background, while hierarchical is more common in the social sciences. Well, whatever you call them, the models will always have both fixed and random effects. The random effects irrevocably tied up into the concept of levels, while fixed effects refer to canonical x variables that you're expecting to predict the y variable, though numerical x values can be considered fixed effects too. They're certainly never random effects, so they could be what's called confounding effects. Okay, sorry, that was getting off into the weeds a little bit there. That was my last video. I won't rehash it here. So that's a little definition on multi-level models. Let us get into typing. What types of multilinear models are there? Well, there are two broad, what we call approaches, multiple regression and structural equation modeling. We will cover and focus on the multiple regression approach in this talk. Within multiple regression, there are three basic classes. First is unconstrained or null. It's really the same as a standard regression or ANOVA that could be labeled as, if we really wanted to, level 1. Then there are random intercepts and random intercepts and slopes, and these both would be considered level 2. Beyond the basics, models can be extended to 3-level models and beyond if you have a feverish and ill-advised desire to build the multi-level modeling Tower of Babel. Then there's also the fact that non-normal distributions can also be fitted, essentially going from a linear mixed model to a generalized linear mixed model. And this approach of multi-level modeling is also good for applications to longitudinal data and also meta-analysis. So I've been chanting about levels, 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 levels. Let me show you some examples to clarify what levels are. So in a basic level 2, individuals are nested in class, aka clustered, aka the random effect is classed. So level 1 down here is typically the measurement you care about, so maybe say individuals. But there's variability that we can account for bringing in higher levels. So like level 2 is going to be some sort of group. In our case example up here, that's going to be classes. Level 3 models, say individuals nested in classes, nested in schools. So individual, I'm going to say this is going to be class, nested in schools. Well, level 3 would be schools. So level 3 and above follow the same extension. Level 1 nested in level 2, nested in level 3. Now, you need to pay attention here, especially getting up to 3 levels. Your high levels may be numbered in a misleading way. So like maybe level 3, the school will be like 1. And then level 2, there's going to be class 1 and 2. And then the individuals, yada yada. Let's say we have our other school over here. So this is school 2. It might also have class 1 and class 2. Do you see the problem here? The levels may be numbered in a misleading way. School 1 has levels 1 and 2. School 2 has levels 1 and 2. This one and this one are not the same. So we will see in the worked examples how to avoid problems while coding. Then finally here, just another example of levels in a longitudinal manner. You might have the individual actually at level 2 here. And then the level 1 is going to be repeats across time. So like T1, T2, T3, and then level 3 would be groups. In this case here, maybe this would be classes at this point. Or maybe we just call it group. Okay, that is level. Let's unroll our blueprints and get cracking on design. Multi-level modeling starts with a good study of design. So first, you'll want your samples to be as representative of the population as possible. Usually that means focusing on level 1 if you care. Now, if you care more about level 2, say a doctor's proficiency rates where level 1 is their patients, it might be better to use a standardized level 1, aka patients, rather than a random sample. That really depends on what you're trying to ask. Now, part of sample representation is going to be dealing with the number of groups or cluster size. Again, groups, cluster size, that's level 2. That's the random effect. There are trade-offs between power and price. So lots of clusters, lots of our random effects variable is better for stats, but it's harder to do. Whereas lots of samples in fewer clusters is easier, but comes out with weaker stats. It captures less of the overall population variety. So, for example, here you might have this is be an ideal design where the green is the clusters and the yellow is individual measurements, individual observations, individuals, whatever. That'd be ideal. Now, you could also have this where there's only 3 clusters. You see there's the same sample size, 30 individuals, but the clustering is very different. Okay. And then moving on here, if you're going to set up a longitudinal study, you're going to need to decide between cohort versus cross-sectional design. So cohorts are better for changes over time because you follow one group of an individual across multiple time points. But the downsides is it doesn't really capture demographic change. It struggles with missing data, etc. However, on the other side, cross-sectional is better for things like population means because you get at each point in time you get a fresh cross-section of people. Though this can be harder to keep up because you need quite a bit more samples than the cohort study. Of course, another design component. In any good experiment, you'll want to make sure randomization is in place. If you're dealing with and this is mostly just for experimental studies or clinical trials, whatever you want to call it. However, if you're dealing with an observational study, that randomization may out of your control. Now then, data design. Make sure you're really understanding your levels. We looked at the example earlier of examples, but you want to make sure you know what's your level 2, how are your level 1s, how's that set up, etc. Where each variable goes, where you're measuring at what point. Then you also want to be understanding your variables. What's your y variable, what x variables do you think predict it? So are they going to be categorical? Are they going to be numerical? And what are those x variables are going to be actually your random effects, your grouping variables? Just give me some sort of category. And that is a big part of designing this, and it really depends on what data you have, what questions you're trying to answer what variables you have collected. After a successful round of data collection, visualizing your data will illuminate your model building path like rose windows. Most steps are standard exploratory analysis, so you can do samples and summaries, like getting the first few columns and rows of your data. You can look at summaries, sort of parsing out what your variables are. Also, histograms are really useful, especially for your Y variable, whether it's normally distributed, etc. You can do it just all at once or across different groups of your random effect, that level 2 variables. There's also correlation, which is helpful to look at how correlated different X variables are, etc. And then, of course, scatter plots. Especially, this is really helpful to do it by level 2 random effects. So we have our Y variable on the axis here, happiness, our X variable, friends, and then this is a scatter plot across groups. So there's 6 different schools. We can see there's very different trends between schools. The same thing is shown for GPA, though the overall regression line is fairly weak in each case. And finally, something that's particularly useful for longitudinal data, spaghetti plots. So dots, those are measured observations, while the line connecting observations are the level 2 random effect. Time to set up the model. Crafting it where brick by computational brick. What your model looks like ultimately depends on your data. So how many X variables are you using? How many levels? What's our interaction terms? So on and so forth. So understandably, there is really no best approach. It's best to start simple and build up. Now, you can start, if you really want to, by formulating the equation for your model. If that really helps you, great. I focus more on how the coding actually is set up, but hey, I'll run through the basis of the equation here. So here is an equation for a generic 2-level model. Let me get my thing here. So Yij refers to the score on the dependent variable for an individual observation at level 1. So the subscript I refers to individual case, while the subscript j refers to the group. So Xij refers to the level 1 predictor, your X variable. The beta 0j is the intercept of the dependent variable, and in group J, so that's level 2. And then beta ij refers to the slope for the relation in group J, level 2, between the level 1 predictor and dependent variable. And then eij is the random error prediction for the level 1 equation. It's also sometimes referred to as Raj. So other than all the J stuff, you really just have a level 1 model if you take out the J, and that'd be the only equation you use. But for 2 levels, we have additional 2 equations to explain the betas. So beta oj has this gamma term, gamma 0 is the overall intercept. It's the grand mean of the scores of the dependent variable across all groups where all the predictors are equal to 0. This W is the level 2 predictor, while gamma 1 refers to the overall regression coefficient, or the slope between the dependent variable and the level 2 predictor. And then the U0j refers to the random error component of the deviation of the intercept of a group from the overall intercept. Then down for beta 1j, gamma 10 refers to the overall regression coefficient, or the slope between the dependent variable and the level 1 predictor. And then Uij refers to the error component for the slope, meaning that the deviation from the group slopes from the overall slope. So as you may have intuited, you can actually create a single equation if you really want to by subbing in the identity of the betas to their respective portions in the initial equation. Well, now that you have gotten over your recommended daily dose of math, ponder how your intercepts and slopes were run. Now, if we throw out the multi-level modeling, you'll just have a fixed intercept and slope like regular regression, shown in this first column here. So you can also give each level 2 group its own intercept, but a fixed slope. So it looks like it here. You can see how the lines has the same slope, but they can be up or down to change the intercept across groups. Further allowing the slopes to vary adds flexibility to the model, so random intercept and slope. So each group can have its own intercept, each group can have its own slope. Now, you could technically also just fix the intercept and let the slopes vary like this, but in practice, that is seldom done, and we won't see that in any of our examples. Okay, let's move on to another topic of setup, centering. Numerical X variable data should be generally centered if 0 is possible in the data or implausible. Really, centering by the grand mean is the standard setup. You can also definitely center Likert type variables and binary. So let's get to that example of centering here. Then shuffling on, we have covariance matrices that can be chosen, especially for longitudinal data. Common types are unrestricted and homogeneous, and then also autoregressive. Now, I'm not going to go into much of the details here, but check out the references for more of the dirt. Finally, you can decide whether you're using maximum likelihood methods or restrictive maximum likelihood methods. Restrictive maximum likelihood is the default in R, and it's better for small samples, and it needs the exact same fixed effects for each model for model comparison. Whereas maximum likelihood is the go-to for different fixed effects. Now, SAS lets you have more options than that, but if you really want to go into that rabbit hole, things like Laplace and like pseudo likelihood, etc. Now, for the moment of truth, getting the computer to do your whim. Several ways to go about it. In R, Limmer and NLME can both run maximum likelihood. NLME is a bit more intuitive for the uninitiated with some of their coding, but I've used Limmer a lot, so I'm going to stick with that. The model is set up here. DV is your Y variable. Predictor is X variable that you care about. The random effect is here. It's going to be this. This is predictor and then ID. This is for random slopes and intercepts. If you just want random intercepts, you just keep this as 1 and not have the predictor here. Also, you can simplify this writing for the slope and intercepts by not having the 1, just have predictor and then your grouping variable ID. Now, 3-level gets a little more complicated, but certainly can be done with 2 parts for random effects here to show the nesting. So day is nested in ID and then ID. You also can set up cross-classified models. Those are ones with independence within individuals, and lower units do not belong to one and only one of the higher level units. So that can happen if you want. I'm not really going to show any examples, but hey, there we go. Now, SAS also works for doing multi-level modeling. Now, here shows an example of proc mixed. I personally use Glimix, and I'll show examples in Glimix, but the coding is comparable. There's random effects go into the class statement to just tell SAS it's a category, not a numerical. Model's built out here, y equals x. This other stuff beyond the slashes are optional, so they're not strictly necessary. And then the random effect is shown here. This is, again, random slopes and intercepts. So there's intercept, predictor, and then sub equals ID. That's our group. If you wanted to just do random slopes, you wouldn't have the predictor here cross that out. There's also a simpler notation I'll show you. And you can do that for 2 levels and cross-classified. Okay then, your computer has spilled out a cacophony of results. What do they mean? So here are some important pieces to look at. There is the fixed effects, with coefficients and significance. There's random effects, and then there's overall model, including AIC or BIC, etc. And then chi-squared over degrees of freedom for SAS. So coefficients, I'm going to show some examples here. So coefficients can be interpreted as slope and intercept, numerical or mean, given all else equal either categories. T-values are the test statistics for each fixed effect. So for example, here we have, these are our coefficients or beta values, and then t-value. Now, the limmer function doesn't, on principle, give p-value, so you're not seeing p-values here. Why it doesn't is whole or bare fish. So you either have to run additional methods to get them or do without. Then looking at the random effects table mainly tells you whether including the random effects accounted for appreciable variance. So you kind of compare the variance found by like the random effect and the residual variance. Here the schools did cover some, but twice as much was in residual, so it wasn't as strong as it maybe other models or other data would have it. And then to compare between models, you want to use AIC or BIC. The lower the number, the better it is, but you don't just, it doesn't really have any good meaning outside of anything else. You're usually comparing models with different AICs to see one has the better fit. So so this is 4438.4. Say there was a level 3 model you tried to use this data and gave it a 4555. You go with this level model as a better fit because it's lower number. Okay, so SAS gives some similar things. It does give p-values for your effects and an overall model f-value. Furthermore, as I've mentioned, it gives this general chi-squared degrees of freedom. It's a level of fit, so it should be around 1. So under 1 is a little bit under-dispersed. Over 1 is over-dispersed. It looks like this one is pretty close to 1, so that's not too bad. Okay, other things you can do to analyze your results. Some of this standard plotting after the fact, residuals, QQ plots, just like you would do for regression. But what's really helpful is having scatter plots with regression lines. So this is an example of just a level 1, this is essentially regression, overall regression line. But then this is fixed, sorry, not fixed, but random intercept and fixed slope. So we can see here this actually changes the comparison comply. There's actually a positive relationship between them. And then this is random intercepts and slopes. You see the slopes and the intercepts vary. So being able to do these sorts of graphs are really helpful for understanding multi-level models and their output. So multi-level modeling is a tricky stack of cards to balance. Here are some caveats and concerns. So you don't always need to use multi-level modeling. So it's best for things like correlated groups, so things with clusters, longitudinal, yes. If the clusters are across time, that's essentially longitudinal. Furthermore, maximum likelihood methods can handle unbalanced and even and missing data better, especially for longitudinal data, better than things like MANOVA or repeater measures ANOVA. Now, when you might not want to use it if there really isn't that much level 2 effects. So if inter-class correlation coefficients, this is ICC, that's one way to tell. If you need to use a multi-level model, I didn't go over it here, you can look more at the references. If the correlation coefficient is too small, it means clusters don't really violate the independent assumption. That is, there's not too much relationship between clusters. And so you could just do fixed effects approaches. That's often good enough. But whether it's a yes or a no, you should have empirical, statistical, or theoretical justifications for using multi-level modeling. For empirical, a big part would be looking at graphs or use the ICC to tell if there might be significant clustering effects, grouping effects. Another one on the statistical side, so clustered and nested data often violate the independence assumption of regression, so you don't want to run tests that violate statistical assumptions. And then also theoretical justifications. If you have a hypothesis or construct that really has multiple levels built into it, you really should use multi-level modeling. So now some more reminders here. If non-normal data rears its head, you want to deploy a generalized linear model. Also, you can treat intercepts and slopes as outcomes of level 2 predictors. And besides histograms, checking for ceiling and floor effects and QQ plots can detect non-normality. On to a tour de force of conceptual examples. Here's an oval example of a 2-level one here. And so let's just do examples here. So that, this might be something like individual at level 1 and then team at level 2. Got our teams. Oops. Got our teams. You got our individuals. This also might be something, individual might be at the level 2 here, and then day, so repeated measurements, so like maybe time 1, time 2, time 3 might be here. That'd be another common 2-level setup. Now for 3 levels, level 1, level 2, level 3, this is how we set up here, so it might be something like individual at the bottom, class, and region. So region is the biggest level, class is nested inside of it, individual is nested inside of class. On the longitudinal side, the individual might be at level 2 here, and then time is again those repeated measures, and then group here up at top. Now one other common multi-level design I want to show you is called the dyad. So there's individuals in sort of grouping. If it's dyadic, that means there's 2 of them, A and B. Maybe you're comparing them, and then the dyad is this higher level, this level 2. Okay, let's get into some worked examples. I will walk through 4 examples of made-up data, both in R and SAS. The data was made in R and then exported to SAS. So if the datasets, I'll have some dataset links available in the description if you don't want to just slog through R simply to get the data for SAS, if you want to use SAS alone. So I'll do example 1, 2, 3, and 4 here, all revolving around dragons of some kind. My first example, like all my examples, are fictional and whimsical to help stick into your head. Plenty other resources have real-life examples of student and GPA and school and so on and so forth. The question my model wants to answer is, does the average number of swords in a cathedral reduce fire damage from dragons? So what I did is I simulated data using a similar method to reference number 9 here, setting different parameters across England and France, though those countries are not actual variable in the model. They're just used for variety. The round-of effect was regions, so 10 total, 5 English, 5 French, and they each had 10 observations. Those are the cathedrals, which measure the average number of knights and archers. These are our X variables of interest. Archers for next example, so bear with me. I centered this data because that's useful, and then I will model fire damage as a function of knights. So let's see here. These are the first 6 observations. See, the fire damage is our Y variable here. These are our uncentered X and Y variables, our region. This is our random effect. So, and then this will be the X variable I'll care about for the first example. So, starting with the unconstrained model or null model, it's just standard regression. In R, so fire damage is as a function of centered knights. So we'll get summary and plot. I'll do the same for SAS. We see here the actual glymics. So the model is fire damage and knights. And I get output for SAS, sort it to get an SG plot, where GG plot here is just from the main data. So outcome here, knights significantly negatively predicted fire damage because this closure was negative, and it was the p-value was significant. You see the same thing over here with the knights and their p-values. So what this looks like, we see his graph here. As the numbers, and then this one's in SAS, as the number of knights increased, the fire damage decreased. Note here that 0 doesn't actually mean 0 knights, but rather, because it's a center data, the average number of knights. So ones on this side is less than the average number of nights, and going higher up is greater than average night. But we can see while this is different, there's still a lot of variability present. Can we do better? Model 2 here with random intercepts. So we're going to add in region as a random effect shown here. We just need the 1 because we're just no slope yet, just random intercepts, 1 over region. Summary, and then I want to create a new variable called fire damage kpred as the predicted variable, so I can graph down below using that. We'll create a plot with regression by region. So the regions will have those different colors. And I can do the same thing with proc limit. So now our class region and then random region. That's what's changed. I'm going to sort this data, do a SG plot. Okay, we have our results here. Nights are still negatively associated, though less strong now. There's a fairly poor fit in SAS with chi-square degrees of freedom. This is a lot higher than 1, but region certainly captured a lot of variance. You can see here that variance in region was over twice that of the residual. So seems like adding our random effect really did on our behalf. So again, as nights increase, fire damage decrease. But now you can see there's different regions have different starting levels of damage. So these are just the predicted variables in a line in R. SAS, a little more fancy. I have the predicted line. We have the raw values and then bands for each region, confidence intervals. Okay, boosting up to random slopes and intercepts. Notice the change in coding of the random effects. So this is the same, but now we have our nights instead of just a 1 here. So it's not a 1 anymore. Nights to get the random slopes to intercept. Make another predicted value, ggplot. In Glimmix, it's a little more complicated by this class. So now in the random, we have to have intercept, then nights, and then a /subject equals region. And then a plot here. This is again still significant, much closer to what we saw with the random intercepts. But it really didn't change much. In fact, the AICC for our level 2, that was 755.5. This one here, or sorry, that's the one here, but the one from level 2, so this is level 3. Level 2's was 7527. This is actually a lower number, so this is a better fit. So I would actually go with just the level 2 random intercepts rather than adding slopes in. It's kind of confirmed by graphs. You can see here that the slopes are a little bit different. You can see them tweak slightly, but really hardly tell. There's really almost no difference between the random intercepts. That model was sufficient to capture the variability. Let's take an aim at a different group in example 2. The same question, but different group of soldiers. Does the average number of archers in a cathedral reduce fire damage from dragons? So standard regression to begin. Yada yada. The only difference is we're adding archers instead of knights. And it is significant, though it's a positive significance, as opposed to the knights, which is not what we're expecting. We were expecting it to be negative because we expect an increase in archers to decrease fire damage. So what is going on here? These graphs suggest that as the number of archers increase, fire damage also increases. But we thought maybe more archers should fend off more dragons and reduce fire damage. So can this relationship really be true? Well, let's get out our crossbows and move up to level 2 to see if random intercepts will help us out. So region is now, again, random effect with random intercept only. We run that. That is now 0, and now it's actually negative, which is very interesting here. Wow. Same like with the knights. So region had a huge impact. You can see here, region covered a lot of variance, was accounted for by region. We plot this. Hey, here we go. As the number of archers in a region increased, fire damage decreased. So the apparent positive curve was wiped away by if we consider region. So that had a real effect here. What about random slope? Let's do some more coding with frumming intensity. We're going to add archers in these and intercepting archers to get random slopes and intercepts. Again, this is significant. And if we look, so this AICs was 752.1, so that was the level 2. Intercepts and slopes, if it was just intercepts only level 2 from our earlier code, that was actually 7623. So this model is a little bit better fit. And we can see here, oh, yeah, the slopes are significantly different. You can see that in some regions, Archer had a fairly weak effect, even possibly a positive effect. But other regions, there's a really strong effect coming out here that the more archers, it quickly reduced damage. Okay, so let's go to a third example. Zooming in from region to individual cathedrals, I next create a new dataset by tweaking reference 10's dataset to answer a medieval research question that I've made up. Does the average number of arrows an archer have influence the average hits an archer gets on a dragon? So just some of the data, I read it in, I subset it, and then I change some variables from like this language post to dragon hit, our arrow number in cathedral, switch things around. Essentially what we have here is we have our Y variable, dragon hit, arrows is our X variable, and cathedrals is our random effect. So then I model dragon hits as a function of centered arrow number. Same thing here. And looks like estimate, p-value, t-value, right on target. Arrow was a significant predictor. You can see here, yep, as the number of arrows increased, on average, the dragon hits increased. So in model 2, I add cathedral as a random effect here. And it's still significant. Can't see it here, but significant over here. A nice chi-square degree of fit in the SAS, though only a fraction of variance is explained by cathedrals compared to residual. So that, and we can kind of see that, yeah, the relations between arrows and dragons didn't vary too much between cathedrals. Random slopes and intercept is next. So adding cathedral, arrows, etc. Again, still significant. The AICC for this one was 2838.5, and the previous one was 2839.4. So this one was better, but only by a little bit. So a rule of thumb is if the difference between AIC scores is less than 2, there's no real difference between the models. So they both predicted about as well. I would stick with probably the simpler intercepts only model. In fact, maybe even just do the level 1 overall. Anyways, here we go with the graphs. We can see the R graph shows that variability was higher at low arrow count, so there's more spread here as the slopes sort of go upward. Whereas at the very highest number of arrows, it's very sort of tightly grouped. Now, I'm not really sure. I tried to plot this, and I'm not sure why the graphs didn't change to show the slopes in SAS. But since I got it to work in R, and the random intercepts versus random slopes were hardly different, figuring out how to get SAS to precisely do this, plotting is a dragon to slay for another day. Dragons. Speaking of dragons, you want more dragons? Well, done. The final data set is tweaked from reference 11, asking the question, does the average amount of dragon gold a knight acquires depend on training time? So I get this in here. I have dragon gold, training time, and this is going to be a 3-level model. So the level 2 is going to be commander, and level 3 is cathedral. And the knight would be like level 1. Or sorry, that's just the ID. The level 1 would just be including training time. Note that eventually I get 2 different, so dragon gold Y, training is X. Knight ID isn't really important, but the commander is important. It's going to be right here. And then cathedral is right here. And then center training. But you notice how there's actually a second commander as well, because commander is nested in cathedral, and the categories, C1 to C2, repeats for each cathedral. there is an overlap that there's more than one Commander 1 because there's Commander 1 Cathedral 1, but there's also Commander 1 Cathedral 2. So this new variable takes that into account, which has C1, 1, and then eventually, if you get down, it would be like C2, 1, etc. And so that helps distinguish C1 from Commander of 1 of Cathedral 1 from Commander 1 of Cathedral 2. We'll see how that plays out in our code. Standard regression, no frills other than level 1. Dragon goal is a function of training time. And looks like that is significant. Significant over here. Training time was significant. What we saw as training time increased, dragon gold increased as well. You can see there's a whole lot of variability. So let's see if we can parse out some of that variability with level 2 random intercepts. Now, commander is a level 2 effect. I use a commander 2 variable here in this case. There seemed to be a pretty big effect of training, of commander and training that covered a lot of variability. And it looks like training time is still significant. We see here, yeah, you can see a commander really has a strong effect. Depends on the commander where you start. That kind of covers a lot of that variability. Now, the moment of truth. Let's bump it up another level. Climb up to level 3. Individual knights. Nested in commander, nested in cathedral. So notice in R, I've set up the model 2 ways. The first just has commander 2, like this, which already has the structure of how commanders are nested in cathedral built in. The second uses the raw commander, but needs additional information, having this cathedral commander to show the nesting structure. Either way, the results are going to be the same. You can actually run the summaries of this here, and they'll give you the exact same output. And then here's how SAS is set up, where there's in the class commander and cathedral need to be there, and then in the random commander is nested in cathedral. And given some of the constraints, I only use S to plot out the results. I use 3 different SG plots by cathedral. And here is the outcome. Yeah, training is still significant. Looks like cathedral had a higher variance than commander, so you can see here over in R. So it looks good that we included three models. Yeah, cathedral had higher variance than commander nested in cathedral. And plotting this here in SAS, cathedrals 1, 2, and 3 starting at different relationships. Commander in cathedral 1 had higher starboards compared to C2 and C3. C3 had the low circle. Now for all the gold in the dragon's hoard, level 3 random slopes and intercepts. Let's go. Training time cathedral, and then another format here, training time cathedral commander, so we have that. In SAS, it's going to be commander cathedral, and again we need to have the random intercept training time and then cathedral. And another random intercept statement here, it's a little confusing, but yeah, commander nested in cathedral. And then I'll do 3 SG plots. These are 2 and 3. C1 was on the other swoop here. Okay, with this, training time does look significant. However, the SAS model didn't produce a p-value, but the f value is rather large, so I think that's significant. Now, likely getting the SAS to properly compute the p-value means changing some of the likelihood methods, a swooping dive for another battle. But what we can say is the AICC was 3353.7 as opposed to the 3384.9 from the last model. So this level 3 random interception slopes is a better fit. There we go. Slope wasn't piercingly different, but you can see it in action. Any way you slice it, dragon gold acquired increased as training time increased. So that was an exciting dragon-infused set of examples. Let's summarize what we learned today. Multi-level modeling deals with data that have non-independent grouping, aka multi-levels, nesting hierarchies, however you want to name it. Not all regressions will require multi-level modeling, so make sure you're trying out the simpler models to see if they adequately fit before you build up. And these multi-level models will always mean dealing with fixed and random effects, and you can decide whether you have intercepts and slopes being random, both, or one or the other. And with careful planning and attention, you can get sophisticated multi-level results. Before going, please take the post-test and the survey. Here are references that I used throughout the talk. And as always, DaCCoTA is supported by the National Institute of General Medical Sciences. So please acknowledge the DaCCoTA in some way if you found this model useful in future research. Thanks for joining, and may all your multi-level models be majestic.